Hello friends, I am Dr. Mallikarjun S. Biradar, Assistant Professor in Mathematics, Government First Grade College, Basavakalyan. Now today's topic is extension of the planar graphs, which we have discussed already in the previous class. Where we left in the previous class, we have considered one theorem. Let G be a connected planar graph with P vertices, Q edges and R faces. Then we need to prove first result, Q is greater than or equal to 3 by 2 R and Q is less than or equal to 3P minus 6. Already in the previous class we have proved this result. How we got this result? Suppose G1 be a connected plane graph of the graph G. For example, this is one plane graph. Now, if we observe one edge is exactly on the boundary of two faces, it implies 2Q, one side 2Q, and if you observe the face, every face is bounded by at least 3 edges, it implies 2Q must be greater than or equal to 3R, which implies Q is greater than or equal to 3 by 2R. So, already we have proved this result in the previous class. Now, we try to prove the other result. Q is less than or equal to 3P minus 6. What is given in the statement? The given statement is G is a connected planar graph. When G is a planar graph, already we know one result by Euler's formula. By Euler's formula, we have proved one result, or we have got one result, that is P minus Q plus R equal to 2. Or you can say R equal to, it is Q minus P plus 2. Say this as equation number 2. Now, but with the help of equation 1 and 2, what we can say? Q is greater than or equal to 3 by 2 times R is Q minus P plus 2. Now, combining the terms of Q and simplifying, it is very easy to see Q is less than or equal to 3P minus 6. This is how we have proved one simple result. Now, we will consider a counter example of this result. So, what is the result? Let us see. Now, we consider one counter example for this. What is the example? Let us see. One example we will consider. Show that if G is a maximal plane graph with a P greater than or equal to 3 vertices, if G is a maximal plane graph with P greater than or equal to 3 vertices and which has got Q edges and R faces, then we will prove two results. One is Q equal to 3 by 2 R and the second one is Q is equal to 3P minus 6. So what is the difference between this result and that result? Of course, maximal planar graph is also a planar graph. Already we have proved for a planar graph, these two results hold. Now, what is the particular case in this? It is a maximal planar graph. Already we know what we mean by a maximal planar graph. This is a maximal planar graph. If we delete this edge, it will be just a planar graph. But if I join these two vertices, this will be one of the example of a maximal planar graph. So now again, as we have observed in this result, again one edge is exactly on the boundary of two faces. And one observation already we have discussed in the previous class, that in a maximal planar graph, the boundary of every face is a triangle. That is another observation which we have discussed in the previous class. So what it implies? It implies 2q must be exactly equal to 3r. In the previous result, when it was just a planar graph, 2q it was greater than or equal to 3r. But here every face is a triangle. For that reason 2q equal to 3r, which implies q is equal to 3 by 2 r. Very easily we got the first result. Now we will think of the second one. So again, that is maximal planar graph. Maximal planar graph is also a planar graph. It implies it has to satisfy Euler's formula, p minus q plus r equal to 2. Or you can say r equal to q minus p plus 2. So using this equation or this result in 1, so what we can say, q equal to 3 by 2 times r. R is q minus p plus 2. Again, combining the terms of q and simplifying, what we will get? We will get q equal to 3p minus 6. So this is the proof of the example. Now we consider another theorem. Of course, it is similar to the previous one, but slight difference. Let G be a connected planar graph with P vertices, Q edges and R faces. If G is a triangle free, this is the additional term. If G is a triangle free, it implies that graph does not contain any triangle. So if G is a triangle free, then we need to show the first result, Q is greater than or equal to 2R, and the second one, Q is less than or equal to 2P minus 4. Now only difference is the sentence is extra. If G is a triangle free. For example, of course, proof of this theorem, we consider one graph which is triangle free. This is one graph in which there is no triangle at all. Every face is other than a triangle. What happens in that case? Again, we consider, let G1 be a plane graph of the planar graph G. G1 is the plane graph. For example, this is the plane graph. Then again, as we have discussed in the previous result, every edge is on the boundary of the exactly two faces. Okay, that is one idea. Another one, if you observe a face or a region, it is bounded by at least 4 edges. At least 4 edges, because it is triangle free. It implies 2q is always greater than or equal to 4r, which implies q is greater than or equal to 2r, which we got very easily. Okay. Again, since it is a planar graph, so therefore by Euler's formula, it has to satisfy p minus q plus r equal to 2. Or you can say r equal to, it is q minus p plus 2. So this is equation number 2. Again using the result 2 in 1, or from 1 and 2 equations, what we can say, q is greater than or equal to 2 times, it is r p q minus p plus 2. Again combining the q terms and simplifying, what we get? We get q is less than or equal to 2p minus 4. This is the result when G is